So this is Chapter 2 of the Inorganic course. We'll look at some basic information on the atom and the periodic table. It's important as a basic understanding to build from. The first 12 pages of the course are material that I won't hold you responsible for. It mostly gives a historical perspective. It's of interest, but it's not absolutely necessary to do chemistry. We start with the first thought on elementary particles around 4000 BC, Democritus, and then 1807, John Dalton proposed that chemicals react in fixed ratios of different elements. He came up with his atomic hypothesis. Around about 1897, J.J. Thomson applied a high voltage to an evacuated tube and noticed a strange purple-colored ray moving through the tube, and later discovered this to be an electron ray. This is called a cathode ray tube. He noticed that the electron ray was deflected by charged electric fields as well as magnetic fields, so electrons were discovered at that time. J.J. Thomson also proposed what's called a Plum pudding model that said that positive and negative charges were more or less equally distributed through the atom. In 1909, Ernest Rutherford came up with I guess what could be said to be a groundbreaking experiment. He fired alpha particles, which are helium nuclei, helium atoms with a +2 charge, emitted by a radioactive material called radium, and directed them towards a gold foil which was coated with zinc sulfide. And the alpha particles, when they struck the zinc sulfide, they would scintillate. That is, they would spark. And you could actually see the path of the helium nuclei. And you notice that most of the nuclei went through undeflected, but occasionally one would bounce back at a very steep angle. And from this he proposed that most of the positive charge in the atom was in a dense center, the nucleus, and most of it was empty space, and that still is valid in our understanding today. Around about 1932, James Chadwick discovered neutrons by firing alpha particles at atoms and dislodging neutral particles, which were identified as being neutrons. And around similar time, H.J. Moseley directed high-energy electrons at various elements, and when the electrons decelerate quickly on impact, they emit X-rays, which produced a photographic image. And on the basis of his images and calculations, he determined that each element, hydrogen, helium, lithium, etc., increased by 1 proton per atomic number, if you will. And then along came the mass spectrometer, still the most powerful analytical instrument we have today. Samples injected into a heated chamber. It's bombarded with high-energy electrons, which dislodge electrons from the sample, creating cations, which are accelerated by a magnetic field and then directed to turn a corner. And of course, the angle at which they turn depends upon their mass and charge ratio. And so by changing the magnetic field, particles of different mass can be directed to a detector at different times, and they come up with what is called a mass spectrum. They're able to identify most of the compounds we can detect today are detected ultimately with a mass spectrum in the highest resolution we can get. And that brings us to page 13, and this is where we'll start our actual study. So you're responsible for the material from page 13 and on. So I know that much of this will be review, but nevertheless I want to go over it. So we know that atoms are made mostly of empty space, but they contain 3 types of subatomic particles: electrons, symbol is E, charge is -1; protons with a symbol P and charge of +1; neutrons with no charge and symbol N. And the protons and neutrons reside in the nucleus, so they're referred to as nucleons. And very important and basic is that atoms are neutral because the number of protons equals the number of neutrons, the number of positive charges equals the number of negative charges, which is why I stated earlier that the oxidation number of all elements in the periodic table is 0. And that's what this basically says here. Now, Take a look at this for a moment, a little digression here. So what's a hydrogen atom made of? Well, it's made of a proton and an electron. And we know that they can be ionized to lose an electron and produce a hydrogen ion. So what is a hydrogen ion? It's simply a proton. And so the term proton is often used in place of a hydrogen ion because it's shorter to write and easier to say. So appreciate that they are the same thing. In fact, if you are familiar with the Bronsted-Lowry theory of acid bases, a Bronsted acid is defined as being a proton donor. That means a hydrogen ion donor, and a Bronsted base is a proton acceptor. And while I'm here, it reminds me of something. Given that the loss of a hydrogen ion means that one electron stays behind, what would be the charge of this polyatomic ion? So starting with carbonic acid, when it deprotonates, when it ionizes and loses H+, the electron remains behind with the carbonic acid or whatever's left of it, which is called bicarbonate, and its charge is -1. And then if bicarbonate, which is still an acid, is reacted a second time and loses another proton, that means it leaves another electron behind and becomes carbonate -2. If I got a nickel for every time a student wrote the incorrect charge of a polyatomic ion, I could have retired 10 years ago. I'm really baffled and befuddled why this is such a difficult concept, which is why I'm explaining this right now. So think about it. If H+ is lost, that means the electron must have been left behind, so the negative charge of whatever was there increments by 1 each time. The three elementary particles, here are their charges: -1 for an electron, +1 for a proton, 0 for a neutron. Here are their masses. Oh, scary looking numbers. Let's work in terms of the smaller unit of mass called an atomic mass unit. Atomic mass units have recently been named as Daltons. Short form is DA, and they are equivalent to atomic mass units. Just spend a moment here. Obviously, you're not responsible for memorizing any of these values, but I just want us to appreciate what is the ratio of the mass of a proton or a neutron to that of an electron. So let's say an average of these is somewhere around 1.008 AMUs for a proton or a neutron, divided by the mass of an electron, 0.00055 AMUs. And we see that the ratio is approximately 1830 times. So protons and neutrons are about almost 2,000 times heavier than an electron, which really speaks to the idea that most of the mass of an atom is in the nucleus. Since 1961, the atomic mass unit was defined as 1/12 of the mass of a carbon-12 atom. We'll talk more about this nomenclature, this notation, in just a moment. And that's the most common isotope or form of carbon. Now, we as chemists or technologists use the unit of grams for mass when we're discussing large numbers of atoms or molecules. So, for example, a mass of 1 mole of carbon atoms is 12.01 grams. Chemists use the unit AMUs for the mass of individual atoms or molecules. For example, the average atomic mass of one atom of carbon is 12.01 AMUs, whereas the mass of a mole of carbon atoms is 12.01 grams. So the conversion factor between grams and atomic mass units is Avogadro's number, 6.022 times 10 to the 23rd. So it turns out that a gram will be one atomic mass unit times this number, 6.022 times 10 to the 23rd. So this now is a conversion factor between grams and atomic mass units. Please take a look at page 14. We're asked to calculate the mass of one atomic mass unit in grams. And we're going to use Avogadro's number as a conversion factor. So I'd write this like this. I'd say how many grams is equal to 1 AMU. And we can use this conversion factor. We want to cancel out AMUs and go to grams, so that our answer will be in grams. All right, so all you have to do is cancel units. If you can, digression, apologies, if you can do this, if you can say A over B times B equals, if you can do that calculation, you can do unit factor method. Is A. We're doing the same thing here, we're just canceling units. All right, so we say that 1 gram is 6.022 times 10 to the 23rd, not enough space, AMUs. Then this we get 1.66 times 10 to the minus 22 grams per AMU. So AMUs are really small units of mass. All right, let's get some practice identifying atoms using their elementary particles. If you look at the pictures, we'll just count them up. In this first diagram on the left, how many protons do you see? Well, I count 1, 2, 3, 4, 5, 6 protons. And the neutrons are the gray uncharged particles. There are 6 of those. The electrons are these small dots that are outside the nucleus, and I see 6 of those. The total charge, therefore, must be 0 because the number of protons equals the number of electrons. And feel free to look this up on a periodic table. This is the symbol C, and it's the element named carbon. In the second atom model, I see a total of 4 positively charged particles, 4 protons, and I see 4 neutrons. And then there would have to be 4 electrons, even if I didn't see them, because we know that atoms are neutral. The charge, therefore, is, of course, 0, and this element is the element symbol Be for beryllium. Check out the spelling on beryllium. All right, the third particle here only has 1 proton. It has 0 neutrons and 1 electron. The total charge is 0, and that is hydrogen. And the last one here has 1, 2, 3, 4, 5 protons, but it has 6 neutrons, lest you think that the number of protons and neutrons is always the same. It's not. And of course it'll have 5 electrons because it's neutral. Charge will be 0. And element number 5 has the symbol B, and its name is boron. There are a few really excellent videos about the atom, and I put some links to these on Blackboard, and I would encourage you to watch them. It really livens up an otherwise rather dry topic. All right, let's talk about isotopes. Are you familiar with isotopes? So take a look at these 2 atoms. The atom on the left here has 1, 2, 3, 4, 5 protons, and that makes it boron. And it has 1, 2, 3, 4, 5 neutrons. So 5 protons plus 5 neutrons makes 5 nucleons, and it's written up here, this is the number of nucleons, or also called the mass number. And then on the atom on the right, it also has 5 protons. It is also boron, but this one has 6 neutrons. 5 plus 6 is 11 nucleons. So here we have isotopes, elements with the same atomic number, but different number of neutrons. So notice the notation that we're using. Number of protons, and above that the number of nucleons. The number of nucleons is a whole number. It's a counting number. And these are called Nuclide symbols. They're symbols for individual atoms or ions. I want to make you aware that there's a similar symbol we often see, and these are called atomic symbols, and they're often written in a similar fashion. So this is the atomic symbol of boron. It has 5 protons, but notice the number up top is not a whole number. That's the weight average atomic mass of the isotopes of boron that are naturally occurring. So that'd be 10.81 grams per mole of boron, or 10.81 atomic mass units per boron atom on average. So you want to keep these two unconfused. So research has shown that not all atoms of a single element have the same mass. For example, all atoms of boron have 5 protons, and that's what makes them boron, but in a sample of pure boron, 20% of the atoms have 5 neutrons, and the remaining 80% have 6 neutrons. And so atoms of the same atomic number, the same number of protons, same element, but different number of neutrons, different mass, are called isotopes. And the ratio of isotopes in naturally occurring boron is pretty much always found to be 20% boron 10, notice the notation, 10 being the number of nucleons, and 80% boron 11. Take a look at this symbol from a periodic table. Here we have this number 10.8117. That's the weight atomic mass of naturally occurring boron. I want to show you how that is calculated and then have you do some similar calculations. So for that, we're going to move ahead to page number 16. So we need to be able to do what's called a weight average calculation. We'll start with some familiar examples. Then we'll go back to our chemistry example. The average bottle volume in this first example, A, would be what? Well, 1 liter plus 2 liters is 3 liters divided by 2 bottles, so the average volume is 1.5 liters per bottle. In example B, in this case, we don't have an equal number of each size, and so the average is not the midpoint, but we can still work it out as the total volume. 2 plus 2 is 4. 4 liters divided by 3 bottles is 1.33 liters per bottle. In example C, we have 3 1-liter bottles, that's 3 liters, and 2 2-liter bottles, it's 4 more, 7 liters divided by 5 bottles is 1.44 liters per bottle. So what I'm doing here is called an arithmetic average. Each volume and each value is given equal weighting, equal importance. We add all of these volumes, divide by the number of bottles. But the same average bottle volume in C could be calculated by grouping same size bottles. There's 3 of the 5 bottles, or 3/5, or 0.6, or 60% are 1 liter, and 2 of the 5 bottles, that's 2 out of 5, or 0.4, or 40%, are 2-liter bottles, so we can actually calculate it this way. We can say the average volume is 1 liter times 3/5 of the total, plus 2 liters times 2/5. That would be 1 liter times 60%, or 0.6, plus 2 liters times 40%, or 0.4. Notice these percentages add to 100, the fractions add to 1, so we know we have the whole sample included here. That works out to be 0.6 plus 0.8 is 1.4 liters per bottle. Same value. If we're given percentages, instead of decimals, we can convert them to decimal fractions by dividing by 100. So here, let's say the average volume is 1 liter, and we'll say 60% of the bottles are 1 liter, and 40% or 20%. Simply divide those by 100, and we write 1 liter times 0.6 plus 2 liters times 0.4 is 0.6 liters, plus 0.8 is 1.4 liters. You want to note that the sum of all fractions in a group equals 1, 3/5 plus 2/5, 0.6 plus 0.4. Just like the sum of all percentages in a group must equal 100%, 60% plus 40%, and so on. In this form of calculation, the volumes of each bottle are added together, but the 2 bottle volumes are not given equal weighting. 60% of the bottles are 1 liter, and 40% are 2 liters. That's called a weighted average calculation. Try this. We have 1, 2, 3, 4, 5, 6, 7, 8. 6 of the 8 bottles are 1 liter, and 2 out of 8 are 2 liters, or 6/8 is 3/4, 2/8 is 1/4, that adds to 1, that's a fraction adding to 1. So 1 liter times 0.75 plus 2 liters times 0.25 is 0.75 plus 0.5 is 1.25 liters per bottle. You've just done what's called a weighted average calculation. Page 17, please. Let's do some weight average calculations on everyday examples that will be, I think, very reasonable to understand and help us with the chemistry example that follow. A survey of first-year college students showed that 40% of the students did not own a motor vehicle, 55% owned one vehicle, and 5% owned 2 vehicles. Calculate the average number of vehicles owned by first-year students. Here I have it graphically. I'd write something like this. I'd say 0 vehicles, and that's 0.4, 40% as a fraction. And then we have 1 vehicle, and the percentage with that is 55%, or 0.55 as a fraction. And then we have a 2 vehicle student group, and only 5%, 0.05. And that would be 0 plus 0.55 plus 0.1, and the total is 0.65 vehicles per student. That's a weight average calculation. Let's try another one. Another survey of first-year college students showed that 5% of students did not drink coffee, 25% drank 1 cup per day, 30% drank 2 cups per day, and 40% drank 3 cups per day. Wait till you get to work. Some people drink a lot more than that. What is the weight average number of cups per day that this survey shows? I would write 0 cups times 0.05, that's the 5%. And then we have 1 cup, and that's 25%, or 0.25, plus 2 cups per day, and that would be 30%. And then we have the 3 cup group, 3 cups per day, and that's 40%. So we have 0 plus 0.25 cups plus 0.6 cups plus 1.2 cups for a weight average calculation of 2.05 cups per day on average. Try another one. A survey of many families in Windsor showed that 20% of the couples surveyed had no children, 30% had 1 child, 40% had 2 children, and 10% had 3 children. Calculate the average number of children per family in the survey. So we would write, well, the 0 children times 0.2 plus 1 child times 0.3 plus 2 children times 0.4 plus 3 children times 0.10. That's 0 plus 0.3 plus 0.8 plus 0.3 for a grand total of 1.4 child per family. So that's not enough. We can't sustain society like that. Folks, you better get busy and have more kids. So notice that, again, the sum of the fractions must equal 1. Right? That means you included the whole sample. All right, take a look at page 18, please. Here's another example. You can skip ahead if this is too boring, but I'm going to go through it anyway. A computer store sells 3 different brands of 24-inch LCD monitors. So far this year, 20% sold for $200. These are the inexpensive ones. 70% sold were $300, and then 10% were expensive at $700. So what is the average cost of monitors sold from that store this year? So it had $200 monitor, and that was 20% of the monitors sold. Then we had this $300 monitor. Most of the people bought that. 0.7, or 70% of the people. And then we had this $700 monitor, and only 10% purchased that one. This works out to be $40 plus $210 plus $70 for a grand total of $320. per monitor. All right, weighted average. Okay, one last example before we do the chemistry example. Here we have data from an auto hauler showed that 35% of the vehicles hauled were SUVs weighing 4,000 pounds. And 40% of the vehicles were subcompacts weighing 2,500 pounds. And the remaining were pickup trucks weighing 3,000 pounds. Calculate the average weight of the vehicles hauled. This is 4,000 pounds with the SUVs, and they were 35% of the total. Then we had the subcompacts, they were 2,500 pounds, and they represented 40% of the vehicles hauled. And finally we had the pickup trucks, and they weighed 3,000 pounds, and that represented what percentage? We had 35 plus 40 has to add to 100. This is 75, so this must be 25% of the vehicles hauled. Would be pickup trucks, so that's 0.25. Remember, the sum of the fractions equals 1, the sum of the percentages equals 100. So I need a calculator for this one, but this works out to be 1,400 pounds of SUVs were hauled, 1,000 pounds on average of subcompacts, and 750 pounds on average of pickup trucks, for a grand total of 3,150 pounds per vehicle. That is the average weight of the vehicles hauled. So you're good with the weight average calculation? All right, so here's a chemistry example. Two kinds of chlorine atoms, or chlorine isotopes, are found in nature. 75.77% of chlorine atoms have an atomic mass of 34.969. Why are they called chlorine 35? Well, that's the mass number, or number of nucleons, and the mass, actual mass, should be close to 35 because the mass of a proton and neutron are close to 1. The remaining 24.23% of chlorine atoms have an atomic mass of 36.966, and that's called chlorine 37. Notice that the nucleon number is close to its mass. Calculate the average atomic mass of chlorine, and then check the periodic table for the answer. So I can write for chlorine 35 that 34.969 AMUs times its percentage as a fraction, 0.7577, plus, for chlorine 37, I can write 36.966 AMUs times its percentage as a fraction, 0.2433. So get out your calculator. That's 26.496 AMUs plus 8.957 AMUs for a total of 35.453 AMUs, or grams per mole, is the weight average atomic mass of chlorine as it is naturally occurring. And I have here a picture from the periodic table. There it is, 35.4528. That's close enough for me, 35.453. All right, so you're good with calculating weight average atomic mass. It's a really important thing to be able to do, not just for calculating weight average atomic masses, but it's used in many areas of our discipline. Let's then go back briefly to page 15 and finish that up. So to calculate the weight average atomic mass, multiply the atomic mass of each isotope by its mass fraction, and then total these up. I get a feeling you know what I'm talking about now. So in the case of boron, we had boron 10, 20%, boron 11. The calculation would be mass times fraction plus mass times fraction equals 10.81, and check it on a periodic table. Well, I think we looked at that already. It is 10.81 atomic mass units, or grams per mole. think I've said this enough times. So this is similar to calculating your final mark in a course. For example, if your lecture mark is 50% and it's worth 70% of your final mark, and your lab mark is 80% and worth 30% of your final mark, then your final course mark, the weighted average, will be 50% times 0.7 and 80% times 0.3 combined together is 59. So in general, we could write a formula like this. The weight average atomic mass of an element is calculated as mass times weight fraction plus mass times weight fraction plus mass times weight fraction, etc., until we've included all the fractions. Some elements have quite a large number of isotopes. In fact, tin and xenon have 9 stable isotopes. I just grabbed something from the web from xenon to show you the fractions of the 9 different isotopes of xenon. Science is complicated sometimes. Let's move ahead to page 19. All right, so this is again kind of a wrap-up. We mentioned there's a notation for nuclide symbols, which has the nucleon number on top, the proton number on bottom, and not to be confused with the notation for atomic symbols, which has the proton number on the bottom and the weight average atomic mass on top. I have here an exercise for you to do. I'll let you do it. I've given you the percentage abundance of the isotopes of carbon and also for silicon and their atomic masses, and you can calculate the weight average atomic mass of each and check your answers on the periodic table. Now you may be thinking, hey, isn't there a carbon-14? Don't we hear about that in carbon dating? Well, you're right, there is, but it's so small that it really won't affect our calculations. That's one of the limitations of carbon dating. It can only be used to date things that are relatively recent, 50,000 years at most, because it's such a small proportion of the carbon present to begin with, and when it starts decaying, it's hard to see after a while. So any longer dates that are quoted in literature talking about hundreds of thousands of years, that would be dated by some other radioisotope with a longer half-life. Which brings us to this right here. Half-lives of nuclides is the time it takes for a radioactive isotope to decay to half its original mass. So here's a problem. The half-life of the plutonium isotope, plutonium-239, that's produced in nuclear power plants is approximately 25,000 years. So if you had a sample that contained 10 grams of plutonium-239, calculate the mass of plutonium-239 remaining after 25,000 years. 25,000 years is one half-life, so you'd simply divide the original mass by 2 because it's reduced by a factor of 2 for each 25,000 years. You'd have 5 grams remaining. After 50,000 years, well, that's 2 half-lives. So you would divide 10 by 2 twice, once for each half-life, and now you're down to 2.50 grams of plutonium remaining after 50,000 years. After 75,000 years, you'll have 3 half-lives. And so the amount remaining will be 10 divided by 2 3 times. Now you're down to 1.25 grams of plutonium remaining after 75,000 years. If you can wait 100,000 years, that would be 4 half-lives. I guess that would be lives. That would be 10 divided by 2 4 times. 3 and 4 is 0.63 grams, which is one of the problems with nuclear power. It's clean, but what do you do with the waste? You can't outlive it, can we? All right, let's look at page 20. There are some problems for you to do on page 20, and I think I'm going to do them with you here now. Oxygen has 3 naturally occurring isotopes, oxygen 16, 17, and 18. Ordinary oxygen contains 99.7587% oxygen 16, 0.0374% of oxygen 17, and oxygen 16 has a mass of 15.994915 AMUs. Oxygen 17 has a mass of 16.999133 AMUs, and oxygen 18, which has a mass of 17.99916 AMUs. Calculate the average atomic mass of oxygen to 3 decimal places. All right, so how do we do that? Well, just like before, right? Mass times weight fraction plus mass times weight fraction for all 3 portions. Now, before we calculate this, we'll need to get the mass fraction of oxygen 18. So if you add up these 2 percentages, 99.7587 and 0.0374, and subtract them from 100, you'll find that the mass fraction of oxygen 18 is 0.239%, or as a weight fraction it would be 0.00239. Alright, so just to save time, I went ahead and wrote it out here. If you care to check calculations, please pause the video and do so. Here's the value from the periodic table, 15.9994, which is okay by me. I was finding this very tedious to do by calculator, so I actually did it in Excel here. I wrote down the isotope names, the masses that were given, the mass fractions, and for this term what I did is I summed up the mass fractions given, and then I subtracted this value from 1 d7. Here's d7 minus d6, so that's the fraction as a fraction, and I multiplied these together, and these were my individual values, and the sum of them here is 15.99938. So take a look at question number 2. We're told that lithium consists of 2 isotopes, lithium 6 and lithium 7. The masses are 6.01512 AMUs and 7.01600 AMUs respectively. If the average atomic mass of lithium is 6.941 AMUs, calculate the percentage abundance of each isotope. That's different. How are we going to do that? Well, let's write an equation to start. So here's what I wrote. For lithium 6, I have its mass times the fraction, which I don't know. That's what we have to solve for. I'll call it x, plus the mass of lithium 7 times its fraction, I'll call that y, equals the weight average atomic mass of 6.941. So how are we going to solve for x and y? We have 2 unknowns with only 1 equation. You need at least 1 independent equation for each unknown. At least that's what they tell us in algebra class. Is there some other equation that we could write, some independent equation that involves x and y we could use? And in fact there is. You could say that the sum of all the fractions is equal to 1, right? That's also true. That'll solve it for us. Now we have 2 equations with 2 unknowns. It should be solvable. Alright, so here to save time I've gone ahead and completed it. So the first equation, I called it equation 1. I rearranged the second equation. In terms of x, I called that equation 2. You remember from algebra class we can substitute. We'll substitute equation 2 into equation 1 here. In place of x, we'll write 1 minus y. And expand this. We'll have 6.01512 times 1 minus 6.01512 times y plus 7.01600y is equal to 6.941 atomic mass units. We'll collect our terms and subtract 7 minus 6 is 1. 6.9 minus 6.0 is 0.9. Y is equal to 0.9251. That's a fraction. As a percentage is 9251, and that was y, which we represented as lithium 7. And then x was equal to 1 minus y, so 1 minus 0.9251 is 0.0749. That's 7.49% of lithium 6. Now when you're done, you should just think about it. First of all, does it make sense? Notice most of it is lithium 7, and if that's true, then the weight average atomic mass should be closer to that of lithium 7 than lithium 6. And in fact, look, the weight average is 6.9, which is much closer to the mass of lithium-7 than it is to lithium-6. So that seems to make sense. You should also check it by substituting those values in. For X, you can write 0.0749 is what we solved for. And for Y, you can write in 0.9251. And go ahead and do the calculation again now and see if in fact you get 6.941. And in fact you will. All right, there's one more to do here. Question number 3 says the weight average mass of gallium is 69.723 AMUs. The masses of naturally occurring isotopes are 68.9257 for gallium-69 and 70.9249 for gallium-71. Calculate the percent abundance of each isotope, just like the last question. So you go ahead and try it, and I'll write out the answer and then I'll review it with you in just a minute. So here's what I wrote for gallium-69 and gallium-71. I wrote the atomic mass of gallium-69 times its mass fraction, which I called X, and that for gallium-71 times Y. And there's the weight average atomic mass. Again, I said the sum of the fractions must equal 1. I rearranged for X. I substituted equation 2 into 1. And here's what I got. Works out. Expanding these terms over addition and subtraction. Then collecting terms. Subtracting. Dividing. Y is equal to 0.399, which represents 39.9% of Y, which we identified as gallium-71. And X is 1 minus Y, or 0.601, or 60.1% of gallium-69. And as a check, you can substitute these two fractions back into the equation, and in fact, you'll find that the weight average atomic mass calculates correctly. So you should expect a question like this on the first test. If we go back to the page that we're looking at, you'll notice that there is a worked solution to problem number 2 sitting right above. Please turn to page 21. Just some more very basic questions. This course will get a little more challenging later on, but I hope you can manage it for now. So we have complete the missing data for these symbols, these nuclide symbols. So the number of protons, I trust you would say 8 there. The number of neutrons would be the nucleon number, neutrons plus protons minus 8, and that would be 9. The charge is given here, it's minus 2. So how many electrons are there? Well, if the charge is minus 2, there must be 2 more electrons than there are protons, so therefore the number of electrons must be 10, 2 more than 8. For a chromium plus 3 ion, number of protons given here in the symbol is 24. Number of neutrons would be 57 minus 24. That would be 33. The charge is given as plus 3. And so the number of electrons must be 3 less than the number of protons because it's plus 3. So that would be 21 number of electrons. Try this one. The element has 38 protons. Now I don't expect you to memorize these. I'll give you a table, something like this, that you can look it up on. 38 right here, this is strontium. So the symbol would be strontium. And the number of protons is 38. And the number of neutrons is 50. So 50 plus 38 makes 88 nucleons. And we're told the charge is plus 2, which is not surprising since the only charge a group 2A metal can have is plus 2. So therefore the number of electrons would be 2 less than the number of protons. That must be 36 electrons. Try the next one. This is element number 34. You look that up on a table. 34 is selenium. The number of protons is 34. The number of nucleons is 34 plus 45. That would be 79. The number of electrons is 36. That's 2 more than the protons, so therefore the charge must be minus 2. And that would be a selenide anion in group 6A, oxygen, sulfur, selenium. So minus 2 was quite believable. All right, the next one has 74 neutrons, 54 electrons, and a charge of minus 1. We have to figure out how many protons it has. If the charge is minus 1, it has 1 more electron than protons, so the protons are 1 less than 54. So it must have 53 protons. Let's find element number 53. I know right where that is. That's iodine. Iodine has 53 protons. It's element 53. We read that the charge was minus 1, so that's an iodide anion. The nucleon number would be 127, looks like. We have chloride. The number of protons is 17. The number of nucleons, 37 minus 17 would be 20. The charge is minus 1. So the number of electrons would be 1 more than the number of protons. That would be 18. I think I want to stop here. The answers to these are given in a couple of pages, so please you finish them up and look at the answers, and if you have a question, make sure you ask me. Number 5 says write the nuclide symbol and state the number of protons, neutrons, electrons for an atom of nitrogen. Well, the nuclide symbol would have the letter for the symbol nitrogen. Now nitrogen is element number 7. You can look it up on a periodic table. That would be 7. And nitrogen 14 is the number of nucleons, so that sits right here. So that's it. So for protons, 7, neutrons, 7, electrons, 7. It's a neutral atom. Likewise, I'm going to let you finish up the last two, and the answers are given on page 22. So let's go there. So page 22 just contains the answers to those questions. And that looks like a good place to stop for this first lesson.